In this video, I'm going to be talking about how to predict where a projectile will land with an elevated angled launch. So every projectile problem has some different variations which make it a little different and potentially a little bit more difficult. So I would consider this problem a little bit more difficult than an angled launch off the ground returning back to the ground. So the first thing we typically do is we usually draw out a triangle, and we have the projectile being launched at 3 meters per second at a 20-degree angle, and we have an x and y component of the velocity, which I'll call Vx and Vy. So I'm going to go ahead and get started finding those two components, and then I'm going to start placing variables into my two columns shortly after. Okay, so as usual, I use sine and cosine. I use the sine of 20 degrees, so I could use the opposite end along with the hypotenuse, my known velocity of 3 meters per second. And then when I did opposite over hypotenuse, I just basically multiply both sides by 3, which would basically be 3 times sine of 20 to get me my Vy, which I put over here as 1.02 meters per second. I did the same thing for the x component, except that I used cosine so that I could get the adjacent side of my triangle, and I got my Vx, which came out to 2.82 meters per second. That makes sense because 20 degrees is not that far from 0 degrees. It's definitely under 45, so more of it is aimed in the horizontal direction, causing this velocity to be a little higher. Okay, so why do we break it up into an x and y column? So it is really important if you're working on any type of 2D projectile type problem to split up into an x and y column, because each of the different axes has a different type of motion. There is no force in the horizontal direction once it's launched, so it's going to be moving at a constant velocity. Therefore, we can only use this formula over here to the left. And then on the right side, we do have gravity acting in the vertical direction. Therefore, it's going to be accelerated motion, and we will use these 3 accelerated formulas over to the right. So over here, I call this Vi because that is my starting vertical velocity. This side, I just called it V because it's constant velocity, so there is no starting or ending velocity. And we always know acceleration is negative 9.8 meters per second squared. Okay, now normally if you're doing an angle launch to where it returns back to the same height at which you launched it at, you could say your initial is 1.02 and then your final is negative 1.02 once it reaches the ground. But it's going to hit that negative 1.02 around here, but then it's going to fall an additional 1.1 meters. So in this case, we can't use a VF of negative 1.02. But we do have an additional piece of information, this delta y over here, which we will call negative 1.1 meters. And then I'm going to go ahead and drop that into my y column over here. Okay, and I'm going to make sure I label that as negative 1.1 because it's displaced downwards in the negative direction from where it was launched. So actually, sorry, I kind of drew this off a little bit. It would be the height from which it was launched, so somewhere around here. Okay, so the launch height is negative 1.1 from the height of the actual launch all the way to ground level. Okay, so anytime we have 3 known values, we can basically solve for just about anything we need with any of these kinematic formulas. And what I'm looking for is my delta x. I eventually want the delta x on this side of my setup, but I am missing a t. I'm looking for my time, and it turns out time is the only connecting variable that can be used in either of the 2 columns because it does not have a direction. So I'm going to take a look at my formulas, and I see that this first formula has a t in it, and this second formula has a t in it. But the first one, I don't have my VF, so I can't use that. So I'm going to go ahead and set up all my values in this second formula and then solve for t. All right, so I found my T, and it's definitely a little bit different than an angled launch where it lands at the same height at which it was launched. So I ended up having this setup right here, where I put in my delta y, my vi times a t plus 1/2, and then the a negative 9.8 times t squared. And I set it all equal to 0. So when you get to this point over here, there are a few different routes you can take. You could go ahead and graph this and then see where your graph intersects the x-axis and hits 0. And then you'll have one negative number and one positive number, and obviously your time would be the positive number. You could use a quadratic formula, or if you have a more advanced calculator, you can just plug this in and then use the solve function. Any of those three ways should get you the time of 0.59 seconds. And remember, that was the time that I wanted over here. So now, after I multiply both sides by 0.59, I'm going to get my final delta x, and my delta x comes out to 1.66 meters. Okay, so if I were to measure exactly how far that was from the table, I'd probably use something like a string with an weighted object from the bottom to see exactly where the edge of the table is, and then measure 166 centimeters out, or 1.66 meters out. Okay, so to sum things up, anytime you have some sort of angled launch, you definitely want to set up your triangle, take your main velocity as your hypotenuse, and then find your horizontal and vertical components. And being sure and careful that you drop them into the two different columns. You have your a equals negative 9.8 meters per second squared as the acceleration due to gravity from the Earth. And then the additional variable that was given in this problem would be the height, and you want to make sure that's a negative 1.1, because in this scenario it was displaced downwards at 1.1 meters. But if it's displaced in the upward direction, then you can go ahead and leave that positive. And then from there, once you run into this setup right here, you may have to use a quadratic or graph it to find your time. And then remember, time is the only variable that can be used in both columns, which worked out nicely for us so that we could find our delta x. And then now we know that the projectile lands at 1.66 meters from the edge of the table. I hope that was helpful in helping you understand, set up, and calculate your final answer for the landing position. Thank you for watching and listening.